Assalamualaikum warahmatullahi wabarakatuh. My name is Sinatu Sadia Syafi'i. Will present and discuss my preliminary research on the rutting behavior of waste steel fiber asphalt mixture. This research were done with my other colleague from UTHM, also from Polytechnic Melaka and Polytechnic Bengkalis, Indonesia. The significant expansion of Malaysia's national infrastructure network over the previous decade has increased road construction. The introduction of asphalt concrete in Malaysia has brought within the problem of the existing quality control testing, which is required to produce such mix to be required tolerance. Even with this material meet the specification, they are often inappropriate in areas of high traffic stress, such as climbing lanes and main junctions, as is evidenced by the rapid permanent deformation along the wheel path throughout the country. This type of deformation was called rutting. It is hazard to road users as it also allows surface water to accumulate, thus increase the risk of water infiltration into the pavement structure. This study discussed preliminary studies on the use and effectiveness of waste steel fibers as an additive in modifying asphalt mixture to enhance rutting resistance. The objective was to evaluate the influence of incorporating steel fiber on rutting behavior by measuring the index of retained strength. It aims to provide researchers with suggestions for subsequent research involving the use of steel waste fiber. This fiber is put into hot aggregate with different rates of 10%, 1%, 2% and 3% by weight of asphalt mixture. The research aggregate were analyzed using sieve analysis to ensure they meet the superpave standard gradation requirements. The test procedure involved drying the aggregate sample in an oven at 100 Celsius for 24 hours before sieving. A dynamic creep test will be used to determine the efficiency of WSF waste steel fiber on hot mix asphalt mixture at UTHM Transportation and Highway Laboratory. The superpave mix design process comprises several steps, the first of which is material preparation that divided into several stages. These studies will utilize the superpave gyratory compactor to prepare HMA samples to evaluate mechanical and volumetric properties as per AASHTO T312. Each sample with 100 and 200 grams of asphalt mixture used for the study. The asphalt binder is then applied until the desired density is achieved. Before adding the steel fibers, the mixture will be manually blended with mechanical blending according to the percentage of asphalt, which is 0, 1, 3 and 5%. This study will prepare 16 samples using 4%, 5%, 5.5% and 6% bitumen with 0, 1, 2% and 3% waste steel fiber added by total mixed volume for specific grades. The performance testing of the asphalt mixture was conducted to evaluate the strength performance of the rutting behavior of the waste steel asphalt mixture. This investigation will employ the dynamic creep test for testing. In this study, each aggregate will be sieved separately before being batched. Dynamic creep test is a vital test to determine accumulated strain, dynamic creep modulus, creep steady slope, and also permanent deformation. A dynamic creep test will be performed to evaluate the asphalt mixture persistent deformation. The universal testing machine was used to conduct this test. The test will stimulate the load of low volume and high volume vehicle with load of 200 kPa. After conducting the dynamic creep test, several rutting parameters were measured to evaluate the performance of the asphalt mixture. The parameters of interest include the dynamic creep modulus, coefficient of stiffness, and permanent deformation. These parameters calculated using the cumulative strain data obtained at cycle of 200 and cycle 3600. The superpave aggregate gradation consists of three components, which is coarse aggregate, fine aggregate, and mineral fillers. The OBC of the specimen was established using 12.5 nMAS. For trial bitumen content of 4.5%, 5%, and 5.5% and 6% were conducted using virgin bitumen to determine the optimum bitumen. Laboratory testing was performed on asphalt mix samples prepared with each of these bitumen contents. Properties of the trial blend were determined and tabulated, as well as the parameters of the asphalt mixture, which is air voids, void in aggregates, also air void filled with asphalt. Based on the obtained egg void content and other considerations within the superpave mix design methodology, the optimum bitumen content for the asphalt mixture is determined to be 5.5%. The selection of this specific bitumen content is aimed at achieving the desired balance of performance characteristics such as durability, stability, and resistance to moisture damage. In this investigation, the performance of 12 samples were evaluated using the dynamic creep test. The sample includes both control and samples with variable amount of waste steel fiber as an additive. At 2,000 and 3,600 circles, the accumulated strength values for each percentage of waste steel fiber were recorded. At the rate of waste steel fiber increase, the accumulated strain decreased, indicating an increase in resistance to permanent deformation. This table shown the summarize the accumulated strain value for each percentage of waste steel fibers, highlighting the decreasing trend with increasing fiber content, also visualized in figure. According to the data of accumulated strain recorded in the table, the control sample had the lowest value of accumulated strain after the maximal cycle. The modified sample exhibit an increasing trend in accumulated strain with the addition of residual steel fiber. The rating performance of waste steel fiber as an additive in the asphalt mixture was evaluated using three parameters: dynamic creep modulus, creep strain slope, and permanent deformation. DCM is a crucial parameter that reflects an asphalt mixture resistant to deformation under dynamic loading conditions. The DCM value demonstrates the relationship between WSF contents and the dynamic stiffness of asphalt mixture in the content of the provided data. As the WSF content increased from 10 to 3%, the DCM values decrease. The graph in figure illustrates how DCM value decreased as the percentage of waste steel fiber increased, highlighting the trend of reducing rutting resistance with increasing the fiber content. This indicates that higher WSF content is associated with a reduction in the dynamic stiffness of the asphalt mixture. In simpler terms, the asphalt mixture with higher WSF content exhibit lower resistance to deformation under dynamic loading. The decrease in DCM values with increasing WSF content suggests that adding waste steel fibers affect the interlocking and binding characteristic within the asphalt mixture. Fibers may create discontinuities of disruption in the asphalt matrix, decreasing the overall dynamic stiffness and a higher susceptibility to deformation under dynamic loading conditions. Therefore, based on the provided data, it can be inferred that increasing the WSF content in the asphalt mixture results in decreased dynamic stiffness or resistance to deformations. This highlights the importance of carefully considering the appropriate WSF content to balance rutting resistance and dynamic stiffness in asphalt pavement design and construction. Based on CSS data value, it is proven that the sample with 1% WSF content demonstrate the lowest CSS value, indicating the highest resistance to rutting amongst the tested sample. This implies that the asphalt mixture with 1% WHF content is less susceptible to permanent deformation under load, making it more resilient against rusting. In summary, the data analysis highlight the impact of WSF content on the rutting resistance of the asphalt mixture. The sample with 1% WHF content exhibit the highest resistance to rutting, while higher WSF percentage, which is 2 and 3%, result in decreased resistance to permanent deformation. The permanent deformation value indicates the extent of deformation or rutting in asphalt mixture under applied load. Higher values of permanent deformation value, susceptibility to rutting and reduced resistance to long-term deformation. It can be observed that as the WSF content increase, the permanent deformation also tend to increase. The asphalt mixture with 0% WHF mixture exhibit the lower permanent deformation value, indicating relatively better resistance to rutting. On the other hand, the sample with WSF content of 1%, 2%, and 3% show higher permanent deformation values. These larger deformation values suggest that asphalt mixture with higher WSF contents are more prone to rutting and exhibit reduced resistance to long-term deformation. This research aimed to assess the strength, performance, and rutting behavior of a waste steel fiber asphalt mixture. The lower percentage of waste steel fiber exhibit lower DCM value, indicating less resistance to deformation under repeated loads. This suggests that addition of waste steel fiber, which is more than 1%, is unable to enhance the rutting resistance of the asphalt mixture. This result is the same as Guo and Jay's conclusion that the stability is unrelated to the fiber. The strengthening effect will only be achieved if the percentage of steel fiber corresponds to the amount of asphalt supply. CSS value demonstrate that the asphalt mixture with 1% WSF contents exhibits the lower CSS value, indicating higher resistance to rutting compared to the other samples. Previous studies also state that mixture susceptibility to pavement rutting corresponds to CSS, with the lower CSS found in the mixture containing 1% steel fiber. This demonstrates that the mix with the lower CSS should resist more rutting. Permanent deformation data obtained for permanent deformation revealed that the control sample, which is 0% waste steel fiber, had the lowest value, indicating better resistance to permanent deformation. However, as the percentage of waste steel fiber increased, the permanent deformation also increased. This suggests that adding waste steel fiber may harm the asphalt mixture rutting resistance and long-term performance. Based on a previous study, using a range of less than 1% is recommended. The study found an increase in performance of 0.3%, indicating the optimal value for using steel fiber as MMA. The selection of the percentage of steel fiber between 1% and 3% yields an unsatisfactory value. Consequently, it is recommended that the rate of use of steel fiber begin at 1% and is far less than 1% to obtain the optimal value for the benefit of added steel fiber in asphalt pavement. That's all for the presentation. Thank you.